Okay, well, I hope everybody's doing all right today. We'll get back to the dot product of two vectors in just a moment. Just kind of wanted to let you know what's going to be happening the rest of this week and next week. Remember, these happy minutes can be retaken up to a 70, just like any other grade, but it's going to be a week after the fact. Now, this one is the only one that's going to be a little unusual. We're going to go ahead and make this one until next Thursday because what's happening next Wednesday? Okay, it's the SAT. Okay, so on that day, they've already told us that they are not going to be given a late start. So even if you're not taking the SAT, you do have to report to school normally. So I'm guessing there's probably going to be a lot of classes meeting in the dining hall, areas like that. I'm actually going to the training tomorrow where they're going to give me some more information. But I know for sure I'm administering the SAT. I believe I'm on the third floor. Okay, so I'm going to get more information about that tomorrow, and I can tell you on Friday a little more if you're not sure. But that means I will not see you next Wednesday. Basically, it's going to be a lost day. I'll see the afternoon classes, but just not you guys. So, if you're taking the SAT, good luck with that. Do the best you can. As far as this week goes, I'm really hopeful that by the end of tomorrow, we should be pretty much done with this set of notes. Maybe a little bit left to take a look at, but I'm hoping on Friday we can come in, finish up whatever we need to, and I can give you time in class to work on your assignment. Now, the assignment's going to be due Tuesday. What's happening Monday? That's the test, okay? So any information from this lesson right here, the dot products, that is not showing up on your test. Okay, in fact, on Tuesday, more than likely, we'll come in, grade the homework, we'll talk about it, then I'll pass back the tests, and we'll go ahead and talk about any problems you guys had with that. What's on the test is going to be material from like the quiz, that first lesson, vectors in the plane, the homework, anything from that, especially the word problems, that's what you really want to take a look at. There's 10 problems on the test, and I think I put 5 word problems on there. Okay. So it's nothing horrible. Okay. In fact, if you're very familiar with how we work those, you should be okay. Probably in the next day or so, I'm going to post some extra word problems so you guys can practice. I just haven't had an opportunity to do that yet. And then next week, we test on Monday. We already talked about Tuesday. SAT on Wednesday. And then, do you guys remember at the very beginning of the school year, the first week, we had to take that district assessment-like test? And pretty much the vast majority of the material you had absolutely no idea how to work, but I said just do your best. Well, now we are to the time where I'm going to give you the exact same test, and hopefully your scores will have improved from the very first time you took it to now. It's the exact same test, same questions, everything, but hopefully now seeing a lot more pre-cal, you'll do better, those grades will go up, and that's part of my evaluation process. So that's what we're doing on Thursday, and then Friday I won't be here next week because I'll be grading internal assessments from my IB students. So it's going to be a fun week and a half getting to spring break, but we're almost there. Any questions about what's going to be happening? No, no. They used to do it in the past. I mean, we've been under different policies, uh, especially when the tax test was around. Based on your scores, you could get incentive pay, things like that. It could also reduce if students didn't do well, but that's really not happening right now. So, no. But I mean, even, if we did have that system, you guys would still do the best you could, right? Yeah, you definitely don't want to go into the test. Well, my goal here is just to screw Mr. West. So I'm going to guess every wrong answer just so he doesn't get paid. His children will be hungry. Okay. There you go. There you go. Just to skew the data. There you go. All right. Okay, so we're going to be looking at some additional word problems today, but dealing with like inclines, work, things like that. That's the majority. What we've been talking about is how to take the dot product of two vectors. We'll review that in just a minute. We just saw yesterday a formula which allows me to go ahead and find the angle between two vectors. And depending on the sign of the dot product, if it's positive, we have an acute angle between them. Negative is an obtuse angle. If the dot product is 0, well, then they're what we call orthogonal. We're going to talk about that term again in just a second, but that means they're perpendicular to each other. And everybody seemed to be doing pretty well with those. So I just kind of want to do one problem with the orthogonal aspect of it, and then we'll go ahead and get into these work problems and these incline problems. Okay, so what's this say? Using mathematical language correctly is important. It's customary to say two vectors are orthogonal, that is, perpendicular to each other. We say two lines or planes are perpendicular, and a vector can be normal to a given line or a plane. So basically what we're saying here is that orthogonal, normal, and perpendicular, they're different terms that can just mean the same thing. Depends on the context that you're using it in. So when we're talking about vectors, I like to go ahead and stick with the word orthogonal. So if we go ahead and are told that two vectors are orthogonal, that means graphically they form a 90-degree angle between them. Okay. So let's see, the vectors u and v are orthogonal if the dot product is equal to 0. And we actually just saw from the previous chart, if the dot product is less than 0, then the angle theta between u and v is obtuse. Okay, so let's try an example. Given vector u equals 4, 6, and vector v equals negative 2k. Find the value of k so that the vectors u and v are orthogonal. Again, means perpendicular. Well, what do we know from the definition above? The dot product has to be what? 0. So this one, we're not actually just showing that two vectors are orthogonal. We know they're orthogonal. We just kind of want to work backwards off this idea and find a missing value. Okay, so I would go ahead and take u and v and take the dot product. So 4, 6 dot negative 2k, and it should equal what? 0. If they're orthogonal, it has to equal 0. Remember, when you multiply two vectors, you get just a numerical value, a scalar. Okay, so in this case, it's just going to be 0. Well, how do we multiply vectors again? I keep forgetting. Okay, so multiply the first two terms. So the a's, so 4 times negative 2, that'll give me negative 8. Now what? Now we multiply the b's, okay, the verticals, so that would be 6k, and then we add them. There we go. So that should represent the dot product of the two vectors, and I know this has to equal 0. We'll see, all I've given myself is just a simple two-step equation. Okay. If I add the 8 over, I know that 6k will equal 8. So this tells me if I divide through, what should k equal? 4/3, 8/6, yeah. There we go. That's all there is to it. If you take the dot product or multiply two vectors, if you get 0, they are said to be orthogonal. They're going to have a right angle between them. Okay. Any questions on that? Anybody have any problems? Okay. All right. Well, let's go ahead and take a look at something a little different. Now, remember in here, we're going to use vectors to kind of, let's say, flirt with physics, but this isn't a physics class, and we're not going to be going into a whole lot of detail. There's actually a lot of things that we're going to be ignoring just for the sake of our problems. But let's take a look at some of these when it comes to vectors. To better understand a geometric representation of the dot product, think of a car parked on a hill as in the diagram. The force vector, okay, due to gravity, F of g, is pulling the car down and against the hill. The vector components W1 equals the force parallel to the hill, and W2 is the perpendicular force to the hill as well. Where the parallel force is the force that keeps the car from rolling down the hill, the perpendicular force is how much force the tires need to withstand to keep the vehicle in place. Okay, so think back. And I'm going to be kind of alluding to what we're going to be doing tomorrow. There's something that we're going to be looking at called this. Does anybody know what that means? Has anybody ever seen that? Okay. This is what we call the projection of U onto V. when I actually project one vector onto another in order to perform some kind of task. Okay, so all I'm saying here is that one of the components that we're going to get is this vector projection. So I'm going to refer to him by name only, but we don't know what he means yet. That's what we're going to spend tomorrow doing. Okay, so think back to those word problems that we did with the original lesson. You remember, like when the quarterback was running or when the ship left the port? You remember those problems? Okay. What we did was we took the component forms of those vectors. In a lot of cases, we called them u and v. Well, once we added u and v, what did we get? What vector did we call it? What letter? R. Remember, we called it the resultant. If we were doing it graphically, we took those two vectors, we used the third side as the resultant. Okay. All right. So using the resultant, we could then find the magnitude. We could go ahead and find the direction angle, any of that information that we wanted, right? Okay. Well, what we're talking about here is that f of g, this one going straight down, the force due to gravity, that is the resultant vector. Okay. So that projection of one vector onto another, that's actually kind of the reverse of what we have here. If we have the two components, we can add them together and get the resultant. So what we have here, what you're going to come to find out, is that this is the resultant. So that formula will allow me to get the two component vectors that create the right triangle. We always refer to those as W1 and W2. Now here, they're using the parallelogram method, but if we were to go ahead and use the triangle, here's W1, and here's W2. See, they're the two components that form the right angle, just like we've been talking about. So basically, in a nutshell, for what we're going to be doing tomorrow, the projection of one vector onto another is going from the resultant to the component vectors, just the reverse of what we have here. Okay. In fact, what you're going to go ahead and see, okay, the resultant vector we have, the force due to gravity, is going to be the sum of W1 plus W2, the two component vectors. It's the same idea. Okay, so this W1 right here, the one that's always parallel to the incline, that's the projection vector that we're going to be working with. Okay, now what does that really have to do with what we're going to do today? Not a whole lot. I kind of just wanted to go ahead and throw that out there because tomorrow is when we're going to spend our time on it. Now, when I was first introduced to these problems, this diagram is great. I kind of set it up in a different fashion. I think I kind of made it a little easier. Here's how I draw the diagram for the same situation. So I always start with a horizontal line, okay? And then I draw my incline, whatever that is. So let's go ahead and say that this dot right here represents the car or whatever object that's on an incline, all right? Well, we've got the resultant force vector due to gravity, okay? There's my f of g. But you'll notice in my diagram, what I like to do, I go ahead and stop it at the horizontal while they go ahead and continue past it. Okay, so what I do here, because I have the resultant, I'm going to go ahead and break it into its component vectors. Remember, those are the two vectors that create the right triangle. Okay, the one that's parallel to the incline, we always call him W1. He's the projected vector. What do we call the one that's always perpendicular to it? That's W2. Okay, well, the reason I like this diagram so much is that whatever angle of elevation you're given on your incline, this little measure right here is always going to be the exact same measure. Okay, and that's what's going to make these problems so easy to work with. Okay, so I think once we get into a problem, you'll see what's happening here. So let's get to an example. Okay. Now, at the bottom of this page, this one says work. The problems that we're about to do don't involve work, so we're not ready to look at that yet. Just go past it to example 4. If the car in the diagram above weighs 2,800 pounds, it's on an incline of 15 degrees, what force is required to keep the car from rolling down the hill? Okay. So I want to know how many pounds of force it's going to take to keep the car exactly where it is. Okay, so I'm going to draw a diagram very similar to the one that I just constructed. I'm going to draw the horizontal. Okay, here's my incline. And let's say that this dot right here is the car. Okay, so here's the force vector of the car pushing down against the incline. In fact, how much does the car weigh? 2,800 pounds. So we know that's the magnitude. Okay. In fact, if you wanted to go ahead and write that as a component form, okay, the force vector due to gravity, it would be 0, negative 2,800. Okay. And you remember, we've actually seen that before. You remember the tension problem where we had that crate suspended in the air and it was pulling straight down against gravity? That's why the value is negative, because it's being pulled straight down. Now, we don't need that in order to solve the problem. I just thought I'd go ahead and throw it out there. Okay. But now I'm going to take this force vector, this resultant, and I'm going to break him into his component vectors. Remember, which one is always parallel to the incline? That's W1. That's what you're going to come to know as the projected vector. Okay. Which one's always perpendicular? That's W2. Okay. So what's the amount of incline that I have here? 15 degrees, right? Okay. So if this right here is 15 degrees, then what's this little angle right here? That has to be 15 degrees as well. Okay. So see, think about what we're trying to do here. This car is wanting to roll down the hill with a certain magnitude. Now, we're measuring that magnitude in pounds, right? So with so many pounds of force, it wants to roll down the hill. So if I knew what that magnitude was, how many pounds of force it's wanting to use, well, what if I had a vector going in the exact opposite direction, let's call it V, that had the exact same magnitude? What do you think is going to happen to two vectors who are going in opposite directions, but they have the same magnitude? What are they going to do to each other? They're going to cancel each other out. Well, if they cancel, what's the result going to be on the car? 0. So it's going to stay exactly where it is. All we're trying to do is find the magnitude of the force the car's wanting to go down the hill, so that has to be the magnitude, okay, that we have to use on our vector pushing up against it. Okay. Well, think about this little triangle right here, the one created using the components W1 and W2. Okay. We could just use a simple right triangle trig equation in order to figure out what the magnitude of W1 is. Okay. We've got 15 degrees right here. W1 would be an opposite, and it looks like 2,800 would be the hypotenuse. So what trig function am I thinking of? What trig function uses the opposite and the hypotenuse? I would say sine. So I could say sine of 15 degrees is equal to W1 over 2,800. Okay. Well, how would I solve this? How did we solve these before? Just multiply by 2,800. Okay. Times 2,800. Okay. Those are going to cancel. So let's see what that is going to become. 2,800 times the sine of 15. How many pounds of force is the car wanting to roll down the hill with? Okay, so let me get rid of that. 2,800 sine of 15. Okay. So I'm getting 724 point, let's say 7. 724.7. Okay. There we go. And that actually turns out to be the answer. Okay. That's the magnitude of W1. Remember, W1 is what we're also going to call the projected vector. Okay. So if this one is wanting to go down with a magnitude of 724.7 pounds, well, if this other vector is going in the exact opposite direction with the magnitude of 724.7 pounds, the car is going to stay exactly where it is. Okay. And that's it. That's all there is to it. Questions? Now, the problem doesn't ask for this, but I'm going to go ahead and show you anyway what's happening on Monday. Remember, that's the exam. Now, this is going to show up on the exam. Not a problem like this, but this formula that I'm going to show you. The only thing we know about this vector V is the magnitude, right? Well, a vector isn't really useful to us unless we have both the magnitude and direction. Okay, so one of the things you will be doing on your test Monday is you'll be using your formula, okay, to figure out what the component form of a vector is given the magnitude and direction. So you remember when we've done this? Okay. I'm going to go ahead and say V equals. So we have the magnitude, 724.7. But I'm going to say cosine of what? 15, because that's the measure that we were provided. Comma, what? 724.7 sine of 15. Okay. Remember, this formula is going to be really important to you, especially when it comes to those word problems. The magnitude times cosine of theta, magnitude times sine theta. This will immediately give you the component form of that vector v, the opposing vector. So again, this problem didn't ask for that, but I thought it was a really good opportunity to kind of bring that up. Okay. Just like we did in all those other problems. And then you can go ahead and, approximate those decimals. Okay, I'm not worried about it here. Okay. So now, one of the sheets actually the only sheet you picked up today had several extra examples. So let's go ahead and try one of these. Okay. This problem is going to be the exact same. Okay. You've got an object on an incline, and you're wanting to know how many pounds of force it's going to take to keep the car from rolling down the hill. In this case, again, ignoring the force of friction, you've got an incline of 30 degrees. Okay. So let's try this one on our own real fast. Let me give you 2 minutes. Okay. Remember, this is going to be virtually identical to the problem we just did. Okay, so you'll want to create the same diagram, everything. And then we'll go ahead and do a work problem, and I think that'll pretty much do it for today. Bless you. Okay, so that's 2 minutes, and you may not be done with it, and that's fine. I've already started drawing the picture, okay, the diagram. So again, let's say this dot represents the car, and it weighs 3,000 pounds. 3,000 pounds. The incline is at 30 degrees. So this is 30 degrees. So this little angle right here is also 30 degrees. Remember, the way we draw this diagram, those two angles will always be congruent. Okay, because you'll also notice the two triangles, they also share that third side. In this case, they'd both be what? What's the third angle of the two triangles? Because all we know so far, we have 30, we have 90, it's got to be 60. Okay, and you can go ahead and put the 60 here if you want to. It really doesn't make a difference. But the projected vector, the one that's parallel to the incline, we always call him what? He's W1. The one perpendicular to the incline, that's W2. Now what I'm interested in is the magnitude of W1, because then I'm going to use some vector, and see, even here in this diagram they're calling it V, whatever you want to call it. We just need an opposing vector of the same magnitude so that the two will negate each other. Okay, kind of cancel each other out. All right, what equation did we set up? Sine of what? So sine of 30 equals W1, the opposite, over 3,000. Okay. And then I would just solve by multiplying through 3,000. 3,000. Those cancel. Now on this one, hopefully we didn't need a calculator. What is sine of 30? It is 1/2. Okay. So the magnitude of that projected vector, W1, should be 1,500 pounds, right? So what's going to be the magnitude required to keep the car exactly where it is? The 1,500 pounds. That has to be the magnitude of the opposing vector V in order to cancel the two out. Okay. All right. How many people got that right? Okay, good, good, good. All right. So it's not too bad, right? Not horrible? Okay. All right. The only other thing, there is another problem here about Mary sitting on a sled, which is on a hill. Same type of problem. I would encourage you, take a few minutes, and it doesn't only take but a few minutes. Try that problem tonight. See if you can find the amount of force required to keep Mary and the sled on the hill from going down. Okay, we'll talk about that first thing tomorrow. But I'm not going to go ahead and do this one right now because I want to show you a work problem. Okay. Now work. The work W done by the constant force F as its point of application moves along the vector V is given by the following. So we're only going to be able to look at one right now because number 2 uses the projection of one vector onto another. And again, I have not shown you that yet. It's actually a very simple formula. But what they're saying here is that we're going to take the magnitude of the force times the distance when the force acts along the line of motion. Now, again, this is one of those things that I kind of change to fit my own needs, something that made it kind of easy for me. I always go ahead and use the force vector, okay? I always go ahead and call it that, okay? Remember that little half arrow above, okay? But what this boils down to is work is going to be the component form of the force vector times, now the component form of the distance vector, I don't use V, I just go ahead and call it AB. Okay? Because for me in my mind, to help me kind of understand this a little better, like let's say for example, we're about to have a problem where you have a crate and like you're pushing the crate across the floor. Okay, so for me to kind of visualize this, let's say there's the floor, the horizontal, and here's your crate, right? So one part of that crate is A, so I'm going to go ahead and push it, and that point ends up at B. So I always think of it as going from one point to another. That's my distance. But if you want to go ahead and keep it as vector V, I mean, really, it doesn't make a difference in the end. Okay, this is just what I've always done. But once you have the component form of those two vectors, you simply take the dot product. That's going to be the amount of work done. Okay, so let's get to a problem. I believe this is example 5. Yes. So it says a large storage container is pulled 25 feet across a warehouse floor by a pulley system using a force of 80 pounds. The direction of the force is 55 degrees above the horizontal. Find the work done. Okay. So remember, the work done is going to be the component form of the force vector times the component form of the distance vector. Okay, so in order to do it, we need to figure out what my two component forms are going to be. Okay. Now, we could go ahead and use that formula that I just reminded you of a few moments ago. You remember magnitude, cosine theta, magnitude, sine theta for both of these? But which one is it actually not necessary to do? Which one do I know immediately? Not the force. The distance, because we're just pulling it horizontally across the floor, right? So how far a distance are we pulling it? 25 feet. So I would say the component form of the distance vector would just be 25, 0. You know, think about like that one problem in the original lesson where we had the quarterback running forward at 5 meters a second. Remember how it was just 5, 0? Same thing here, it's just distance. Now, if you wanted to, because we're horizontally moving, what's the angle of elevation? 0, because it is remaining horizontal, correct? So you could go ahead and say, you know, 25 cosine of 0 25 sine of 0. You can still go ahead and apply the formula to it. Okay. But what is cosine of 0? 1. So 25 times 1 is still 25. What's the sine of 0? 0. So 25 times 0 is 0. Okay. So with those horizontal and vertical vectors, you could just go ahead and put it together, but if it makes you feel better, yeah, go ahead and use the formula. Now, we can't quite do that with the force because this one we're actually going to have to calculate the values. Okay. What's the force being used to pull the object? 80. So I'm going to start this component form by saying 80 times what? Remember, it's magnitude times what? What trig function? Cosine theta. So in this case, it's going to be cosine 55. Okay. And then what should the second part be? This is the horizontal. What's the vertical? Oh, but we're missing one thing. We still need magnitude sine theta. Okay. Is everybody okay with that? Okay. Well, why don't we go ahead and figure out what that approximation is going to be, what the decimal value is. So let's come on over here. Let's get rid of, I'll leave it here. 80, and then we had cosine 55. So let's say 45.9, just go ahead and put something on my paper. And then we need 80 sine of 55. Okay, so let's say 65.5. Okay. All right. And I just completely blanked on that. What was 40 what? 45.9? Okay. 45.9. I think that was 65.5. Okay. There we go. So I've got the force vector component form. I've got the distance vector component form. Any questions on how I got those? Okay. And work is very simple to find. Work is just going to be a dot product or a product of the two. So there's the force vector, 45.9, comma 65.5, multiplied against the distance vector, 25.0. And actually, why does this even turn out even easier? What's one thing I don't have to worry about? Because how do we multiply two vectors again? We multiply the A's, we multiply the B's. So if I were to write this out, this would be 45.9 times 25 plus 65.5 times what? 0. So anything times 0, that just disappears. So that's all I need. Okay. So while I've rounded it for my paper, I'm going to use again the exact value in my calculator. So I'm going to go ahead and take this guy right here times 25. So I'd say it's going to require 1,147.2 foot-pounds of force in order to move the object across the floor. Now again, foot-pounds, you can convert that if you want to. I'm not interested if you're one of the physics students and want to do that. But I would just stick with this. Okay, 1,147.2 foot-pounds. Anybody having a hard time? Any questions? All right. So 1,000, what was it, 147.2 foot-pounds. Okay. Now you'll notice you have a couple of extra work problems here. Our time is almost up. Wow, time really does fly when you're having fun, right? In math class, it always goes fast. Okay. Anyways, while you're taking a look at that one problem with Mary and her sled sitting on the hill, take another minute or two. Try this one here about the gentleman pushing the vehicle. Okay. Find the amount of work done in joules to move it 10 meters. Okay. So I'll have those problems worked out when you come in tomorrow. I'll go ahead and show you, answer any questions, and then we'll go ahead and move on with vector projection. Okay. All right. Good. Okay. Well, if you can get my calculators up to the front, please.